All right, now we're going to look at the next part of Chapter 4. So we're just going to talk about the experiments here. All right, so we started off this chapter by talking, or this section by talking about observational studies versus experiments. So in an observational study, you're just observing something. You're not actually trying to change anything. In an experiment, you're actually imposing some treatment in order to change something. So if you want to understand cause and effect, you need to do an experiment. If you just want to observe something, then you can just do an observational study. Observational studies often fail because of confounding or lurking variables. So they're kind of the same thing. A lurking variable, so it's a variable that's not among the explanatory response variables in a study, but may influence the response variable. If you don't do something to control for the lurking variable, then the lurking variable becomes a confounding variable. So confounding occurs when two variables are associated in such a way that their effects on a response variable cannot be distinguished from each other. So when we design an experiment, we're trying to make sure we control for those lurking variables so we don't end up with any confounding. So I had an example in class about a soccer coach. The soccer coach put his team on a new workout program, and their playing ability improved, but at the same time the team was taking vitamins. So the vitamins are the lurking variable, so he doesn't know, is it the vitamins that cause their performance to improve, or is it the increased, the extra practice time? All right, we had some terms here for experiments. We had our treatment, which is what was being applied to the individuals of the experiment. We had the experimental units, and that's who the treatment's being applied to. They didn't have to be humans. They could be light bulbs or batteries or things like that. The book says that if the units are humans, they're often called subjects, but I don't know that that's always true. So the experimental units are who the treatments are getting applied to. The treatment is what's being manipulated. The explanatory variables are called factors. Many experiments study the joint effects of several factors. In such an experiment, each treatment is often formed by combining a specific value, often called a level. So this is just kind of, so here's an example about SATs. So they are exploring using an online version of this course. The online group gets an average score of this. It's higher than the long-time one. So if we wanted to go through some of those terms, the experimental units would be the students. The treatment is taking the online course. The response is their score in the end. The treatment, so it's the online course, so that's the treatment again is usually the same thing as the explanatory variable. And then the factors also the same thing in this case, and the level in this case there's just the one level looks like. So this example that they just went through, they just had the experimental units that were getting the treatment, they were getting the response, and then measuring the response. There was no control group here. So most of the time we try to make a better experiment with a control group. So what we try to do is we perform a comparative experiment. So some units receive one treatment and similar units receive another. So most well-designed experiments compare two or more treatments. So comparison alone isn't enough. If the treatments are given to groups that differ greatly, bias will result. So we randomly assign the people to the groups. So we talked about a completely randomized design where the treatments are assigned to all the experimental units completely by chance. So we may have a control group that receives the basic or baseline treatment. So if you remember, we made these flow charts. So you always, and you wouldn't leave it generic like this on the AP exam. You would actually write out what you had here. You'd write your random assignment. You'd write your group 1, how many people in group 1. write out group 2, how many people are in group 2, treatment 1, and what is it, treatment 2, what is it, and then compare, what are you comparing, so you'd be more specific. So randomized experiments, those are completely randomized, those are the most basic ones. What you're trying to do, in order to create a good experiment, you're controlling for lurking variables. So when you use that comparative design, you have one group receiving the treatment, the other group not receiving the treatment, or like a placebo. You have random assignment, so the groups look the same when they start off. So hopefully when we are done, we know that it's the result of the treatment, not because one group was already smarter in the case of the SAT, or healthier if I was testing a drug than the other group. And then replication. So I try to make sure I repeat this in several units so I can actually get reliable results. All right, here's another example here. In this example right here, they're actually doing, I think they were measuring heart, like heart performance or something like that. But anyways, a couple things here. So they had a treatment they were giving. The treatment was a combination of aspirin and beta-carotene. There's actually 4 treatments then, because you could have yes aspirin, yes beta-carotene, and so on. The treatment or the explanatory variables, there's 2 factors here, because one of the factors is aspirin, the one factor is beta-carotene. The factor has 2 levels. It's either yes or no. Factor 1 has 2 levels, yes or no. And again, it comes up with these 4 treatments here. In this experiment, they randomly assigned people to these different 4 groups. They have a control group here so they can know, both placebo for the aspirin and placebo for the beta-carotene. They have other treatments as well that they can compare it to. And then they were replicating it on several people. I've said before, you want to make sure that your subjects are treated identically. The response to a dummy treatment is called a placebo effect. Whenever possible, it says you should experiment with subjects should be double blind. So you're double blind that's when your subjects nor the people who interact with them and and measure the results know what treatment a subject has received. Obviously, the person analyzing all the data knows the treatment, so they can analyze it, but the subject doesn't know that he got the placebo or the aspirin, and the person giving out the pill doesn't know what one they're giving. When we get to this point later on where we're ready to do inference, we're hoping to see a difference in the response that's so large that's unlikely to happen just because of chance. So when we look at that difference there, we use our probability. So if you remember this, when we did our hypothesis chapter, we calculated p-values. And based on what those probabilities were, if the difference was so large that it was unlikely to happen by chance, then I said the result was statistically significant. We also talked about another type of design. It was about blocking. So maybe if you have groups of people that are going to react similarly to your treatment, you might want to block on them. So maybe you want to block on gender, or you want to block on their health or their exercise activity. And then in a randomized block design, we have our blocks, which are not assigned randomly, but then after that we have random assignment. We also talked about a matched pair. So we could, in a matched pair, it's kind of like a block design, but each block, it consists of matching a pair of similar experimental units. So in class I went over like an example with boots, and you had a treated boot on one foot and an untreated boot on the other foot. Also, when we think about like an SAT score before a test and an SAT score after a test or after a class. So before the class, and then the SAT score after the class. When you do that before and after, those are matched together, so there's a pair there. There was an example here. So again, we have observational versus experiment. We have our treatments, which are applied to the experimental units, sometimes called subjects. There was multiple types of designs we talked about. We talked about completely randomized, block, and matched pair. We're always trying to control. We always randomly assign, and we replicate. Sometimes we can be double blind. Usually we give a placebo to control for the confounding. And like I said, we do blocks or matched pair. Then section 4.3 had a couple things in it. Not a lot of this is on the AP exam, so I don't want to spend too much time with it. The big thing here is that you just need to remember when you can actually infer something about the population. So if the individuals are randomly selected and you randomly assign them to groups, so you're very controlled there, then you can infer something about the population and you can infer something about cause and effect. If the individuals were randomly selected but you did not randomly assign them to groups, you can still infer something about the population, but you can't infer anything about cause and effect just because you didn't control in the assignment. If the individuals are not randomly selected, but they were randomly assigned to groups, you cannot make inference about the population, but you can make inference about cause and effect. It just only applies to that particular group. And then if both are no, then you can't make any inference about the population nor make any inference about cause and effect. And some of this other stuff is just about the practicalness and the ethicalness of experiments, and those are not questions that are going to be asked on the AP exam. And that's it for Chapter 4 now.